Hello everyone, thank you for joining. In this video we're going to talk about, again, Einstein's special theory of relativity, but we will look at the events and the measurements. Last video we've seen that delta t was not equal to delta t dashed. And that's a very peculiar nature of time, and we will talk about time dilation again at some point. But first, let's understand these terms. What does event and measurement mean? Well, the event simply means that it's a physical activity, right, that takes place at a definite point. So I'll say definite point in space and time. Now, the definition will have definite here, and in fact it will say definite time here. Okay, so different observers might perceive an event at different times and different positions, but it is not saying that the event itself is not definite. So we're not really, as I said, the name relativity is a bit ironic, and Einstein he's after a definite and the absolute certainty, right? Okay, and now we will have a new conception of space and time, and to begin with, we need to consider how we measure anything in this space and time. Yeah, so now we have been talking about reference frames. So this is S, that's the reference frame. So what we're going to do is we're going to assume that this reference frame is made up of, it's like a cubic lattice. It's made up of meter rulers and clock everywhere where the rulers meet. Yeah, so these circular objects are clocks. Okay, and this length here is a meter ruler. I mean, it could be as long as you want or as short as you want. Yeah, and the event will be, let's say we have a firecracker exploding at this point here. When did that happen? Well, we will look at the closest clock to that event and notice that the length is arbitrary, so we can use a meter ruler, or it's a arbitrarily small object, but this is just to give you a rough idea. And so this will be the actual time of the event, and then the observer at this point, let's say we have an observer and observer at that point, they will perceive the time to be different. Yeah, but the good thing about it, that we could go back in time. Still, we are in the deterministic reference frame, so we could go back in time and find the actual time when this event took place. Yeah. So to do that, to be able to go back in time, we need these clocks to be synchronized. So you can picture it as that we have this giant master clock at the origin, and let's say the clock shows that let's say it's 3 o'clock here. Yeah, that's 3. So yeah, 3 o'clock. So we have apologies. So we have 3 there. In other words, every other clock in the space would be imitating exactly identical to that master clock at the origin. Okay. Now, one thing to consider is that when the event takes place, we're not assuming time to be 0. We're not taking that t we're not taking t to be 0 if any event happens. Yeah, so you have a master clock, and every other clock is just identical to that clock, right? And this is what the synchronized means. So these clocks, every clock is indeed synchronized. Okay, that's the meaning of synchronization. And of course, this is just an idealization. So there are no clocks, there are no meter sticks in each reference frame. It is just imaginary, and therefore information can pass through these points with no problems. Yeah. So the most important thing here is to notice that we call, let's say, the event happen at time t, right? So t is the time at which the event actually happens, not the time at which the experiment sees the event. That's important. An event has a unique set of space-time coordinates in each reference frame. So it is unique, yeah? Right. So we have this idea of event now, and we have this idea of measurement. With that, there comes this new picture of space-time. Now we talk about space-time coordinates rather than space coordinates, and these clocks are synchronized. Yeah. So let's do an example to a question. Let's solve a question to understand, a very simple question to understand the very basics of this theory. So let's say we have an event here. So, and we have two observers. One person stands here, person A. The other person stands there, person B. Let's say this is 900 meters from the origin. Let the first person, A, to be at the origin, yeah? And then we have some explosion taking place here with some coordinate, space-time coordinates xt, yeah? So, and then what happens is that it takes, let's say, t is equal to 3 microseconds to reach the wave fronts, so light waves to reach the observer 1, and it takes let's say 4 microseconds to reach the observer at A. Right. Okay. And the question we want to answer is, what is this time? And also, what is x? What is the space-time coordinates of this event? So can you figure out what x and t are? Right. So if you like to pause the video here and try this question yourself, and then we could go over it together. Just to say it again, the 4 mu s is the light reaches this person. Light wave, you can think of it as in, spherical expansion. Okay, so let's see if you can work out what is x and t are. So, right, now let's think about it. Now, the light we said travel 300 times 10 to the 6 meters per second. We can write it as 300 meters per microsecond, yeah? Okay, so, and that is, that's a good, useful information, because that implies that it will, we can start counting time in 3 microseconds, isn't it? Yeah. So, right, that means, well, since it is taking, let's think about it first of all without any equations. So if it takes 3 microseconds, now one might think that the distance must be, 300 times 3, which is equal to 900 meters. Yeah. Well, because you might say, the light is traveling 300 meters per microsecond, and therefore it will have to travel 9. And similarly, you could go back here and say, this must be 1200 meters, because it's 300 times 4. But as you can clearly see, this is 900 and this is 0. You can't fit in 2100 into this. So that's the idea of when event takes place. Let's say event is taking place here. What time was it here? That's what we're interested in. What was the time when the event takes place? Yeah. remember, we're interested in the absolute certainty, the definite time, right? So, well, one way to think about this is we could simply guess, right? Because if you think about it, if you're familiar with the relativity, you can simply see that t will have to be 2 here. Why is that? Well, if t is 2, that means it will take 2 to 4, it will take 600 meters that way, and 2 to 3, it will take 300 meters that way. So in other words, that would be, this point would be here 600 meters, and it fits in with the rest of the picture, isn't it? Yeah. Okay. But to solve it properly, we say we look at this distance from there to there. That point is x, so we have x minus 0. That must equal to 900 minus x. So 900 minus x is that bit here. Okay, 900 minus x. But then, of course, we have a... So since the light is taking 1 microsecond more to reach A, we balance this equation by adding the distance traveled by the light in 1 second, right? And if you solve this equation, we have 2x is equal to 1200. That implies x is equal to 600 meters, as we've guessed, right? So remember, we're adding 300 here because it takes 1 second more to reach observer A. To balance the equation, we know that light, sorry, not 1 second more, 1 microsecond more. To balance the equation, we have to add the distance traveled by light in 1 microsecond, right? Okay. So, right. So that, since this is, now we know it's 600, yeah, it must have taken 600 meters, it must have taken, if it's taken 4 microsecond there, so the beginning, we must have t to be 2 microseconds. So the clock was reading, so the actual time, the definite time, is that t is equal to 2 microseconds, right? So, so in other words, as you can see, two different observers observing 2 different times, but the actual times the event took place is not relative. It is definite. That's t is equal to 2 mu s. Okay, right? Okay, so we will do one more thought experiment about simultaneity, how the idea of something being simultaneous in the next video. And then we will look into time dilation. Yeah, I hope you enjoyed it. I hope you found it interesting. Thank you for joining, and I look forward to seeing you in my future videos. Thank you.